My name is Huang. I'm from University of Texas at Austin. I'm here to represent our group, Dr. Alvaro Cardenas from University of California, Santa Cruz, and my advisor, Dr. Ross Boddick from UT Austin. So as the title said, in this presentation, we're going to look at the IoT, the cyberattacks on the IoT devices, but from a different perspective. We're looking into power systems and how does this cyberattack impact the operation of the system and how the protection design in the system defend the system against such cyberattack. So cyberattacks in the power system existed before. It's actually happened in Ukraine power grid 2 years in a row from 2015 to 2016. Caused over 100,000 customers lost their power supply for a long time. And then there are evidence showing the footprint of cyber attackers in the nuclear plants in the US. And recently, if you follow the news, between the US government and Russia, there's an escalation of a potential cyber warfare on the power grids. So the previous power grid attacks are targeting the bulk power system, the control center. So typically, there's this supervisory control and data acquisition system that collect the data from the power systems. And then the engineer works with the operator inside the control room. And then they will send some commands back to the system to operate the system. So it has become a target to the cyber attackers. Then they will try to illegally get entry to the system, and then they will launch the denial of services, try to block the people in the control room, and then they can take over the system, do whatever they want. Recently, we have this discussion about new type of cyber attacks on the power system, targeting the consumer's Internet of Things. So Internet of Things become popular nowadays. People just download apps and they can control some home devices with their smartphones. And then, given the convenience of the modern life like that, they at the same time expose many of their devices on the internet. Particularly, those ones consume a lot of energy. For example, your fridge, your electric vehicles, or ovens or water heaters. So that can give a chance that cyber attackers can control them. And if the cyber attackers can collect a large amount of them, they can manipulate a significant amount on the demand side of the power systems. So this issue has been discussed in the previous work. One of them presented here in this conference last year. So now the question comes to what are the impact of the cyber attack on the IoT devices to the power systems? Can they really bring down the operational power grid? Unfortunately, from the previous work, the answer seems to be yes. So we think this is a very important issue, and we look into this problem and try to do simulations with our tool. And our result is slightly different. Although we think it's important to pay attention for such cyber attacks, but to bring down the power grid is not as easy as previously thought. So what are the reasons make our work different, results different with the previous work? So we group them into two categories. So first, the way we model the protections in the power system are different. And then secondly, we operate the simulation different. Due to the time limit, we're going to focus on the protections of the power system in this presentation. So the outline of the rest of the presentation goes as follows. We're going first to discuss the impacts of Mad IoT attack in details on the power system. And then we're going to show what is protections in the power system and how does they work. And in the end, we'll show two different case studies to demonstrate the operation of protection and the coordination of simulations. So once the cyber attackers compromise the demand, one thing they can do is to increase the demand. So then some power plant have to increase their output to supply that extra demand in the system. So what is dangerous is some of the transmission line may get overloaded, and then there's a chance that they may they are taken out. So we're going to discuss the detail of protections on the transmission line later in this presentation. But at this point, we just have to know if the line is severely overloaded, there's a chance that the line will be taken out. And then the power flow used to flow on that transmission line now goes to the neighbor transmission line, and then increase the burden of those lines, and then impose the same danger to those lines. And then this kind of cascading outages can spread into the system, potentially can lead to a blackout. So that's one part of the impact that Mad IoT tech can put on the system. The other impact from the Mad IoT tech is they can cause the energy imbalance in the power systems. So in the next few slides, we're going to show what is the energy balance in the power system and why is that important. So the bottom line in the power system is to store electricity in long term, in large scale, are still not economically efficient yet. So what does that mean is we have to match the demand with the generation in real time in the operation. So in the middle, in the modern power system, we have these large generators. Then they have those rotating mass inside the unit carrying the magnetic field. That's the way they convert the kinetic energy into the electricity. So those rotating mass, they are electrically coupled, and they can provide some inertia to the system. What does that mean? So when you go back home and turn on your light or your AC, no one tells you when to do that, right? So it's unexpected by the generators. They cannot increase their output instantly to match that demand. So before they come in and react, those rotating mass inside the generator will reduce their speed a little bit so that they convert that little bit kinetic energy to the system to supply that electricity demand. So now you can understand how the Cybertek can put in, cause the energy imbalance in the system. They will increase the demand, and then suddenly we have more demand than generation in the system. So a lot of those rotating generators will start to slow down, and then you can think system frequency as a representative of the average speed of all the units in the system. So the system frequency will start to decline. So why is that a bad thing? All the generators cannot operate at any frequency. So they have a safe range of frequency that they can operate. Otherwise, they might have permanent damages on their very expensive devices. So what they do in this condition is if the frequency goes out of the limit, they may take out their generator from the system. But that's a horrible thing to do at this moment because on one hand, we have this actual demand put on the system, and on the other hand, we're losing generators. So the result is the energy balance are getting worse, and then eventually the frequency will decline faster, and we're losing more generators, so there's a danger that we may have a system collapse and lead to a blackout. So next, let me introduce the protections and to have some discussion how the protections are designed to prevent such consequences. So I would like to divide the system protections into two groups. There are protections designed to protect the local components, like the one we mentioned in the generator. They don't allow their unit to operate outside of the safety range of the frequency. So they will disconnect their unit from the system. And there are other type of strategy designed in the system to protect the system at all from failure. So they apply this so-called N-1 criteria that is commonly applied to all the power system, most of the power system across the world, meaning taking out one out of N components in the system shouldn't lead the system to a large failure or losing power supply to customers in large area. So we're going to talk different type of protections in the rest of this presentation. But before we go to the result, I would like to briefly introduce this cascading outage analysis tool that we have been developing for different generations in our lab. So we designed this tool to study the power system reactions to the large-scale disruptions. So we model different type of protection schemes, including the two we mentioned in the previous slides. And we study the system dynamics, and we represent the power flow on the system. So if you're interested, please check out any of the publications we have about this model. So now let's move into a small case study. So for this small system, we have several small generators and then several demand, and there's a small transmission system to connect the generator to the demand. And now Cybertek comes in, and then they control the demand, increase the demand by 15%, and then we spot one transmission line get overloaded. So now is the time to clarify what does overload mean. So once the transmission line get overloaded, there are actual power flow on the transmission line than what they designed for. So what happens, they will generate more heat along the transmission line. So the transmission line will start to sagging. And the sagging itself is not dangerous. What is dangerous if it is sagged too much, there's a chance that may attach to the ground object, like the tree branches, and cause short circuit fault. That's something operators should prevent for. So normally operators will allow some margin for the transmission line to go overload. So I think the takeaway from this slide is the overload of transmission line doesn't mean we have to take out the transmission line immediately. So what we modeled is we have this time inverse protection schemes. Given the magnitude of the overload, there's a time index return telling us how long should we wait until we take out that transmission line from the system. So now let's take a look at the frequency footprint of this Mad IoT load increased attack in this small system. So the Mad IoT load increased by 15% at second 1. And if you remember 10 slides ago, we're talking about the energy imbalance. So we have more demand than generation in the system. So those units have to be slowed down to supply the demand. The frequency start to drop. And then we have this under-frequency load shedding strategy to protect the system. Under-frequency load shedding is designed for the case when the frequency goes down. Frequency goes down because we have more demands than the generation in the system. So it makes sense for the system operator to deliberately disconnect some load to rebuild the energy balance, and then they would bring back those disconnected loads gradually later. So after 2 under-frequency load shedding, in total 15% of system load are disconnected, and then system reach to a new balance, and then the frequency goes stable. And because of that countermeasures, the power flow inside the system are changed. So the previously overloaded transmission line right now is relieved. And now we can look at the case study in a large power system. So we take this case with over 5,000 buses, and I want to mention that although we're trying to approximate how the power system reacts to large disruptions using the protection schemes, but we do not intend to replicate the protections in the real system because it's an impossible thing to do, and also it's not ethical to do. We have a bunch of assumptions. So IoT attacks, they will take full control of the demand. They increase and decrease the demand simultaneously. And also, the portion of demand compromised are evenly distributed in the system. So what if we increase the system load by 1%? Then we look at the frequency on the left. We can see the frequency goes down, but if you look at the number, it doesn't go down that much. And then the system will remain stable afterwards. The power flow on the right-hand side doesn't change that much. So that gives us a result different than the previous conclusion, which lead to a large-scale cascading. So if we scale up the attack to 10% of system load, now we find that the frequency go down to the level that some of the under-frequency load shedding will take action and disconnect some load. And the power flow on the right-hand side increase because of the load attack, and then will decrease again after under-frequency load shedding. We have more results included in our paper, but due to the time limit, we have to stop here and make a conclusion. So from the previous work, they did a very interesting work about Mad IoT attack on the power system. Described as a die picture of the security of the power grid with the frequency instability and cascading line failures. So we think the negative impact of Mad IoT attack in the power system for sure is important and should be paid attention. But for now, it seems not as dire as originally thought. And there do. Although we're a little bit optimistic at the point about the current system against the IoT Cyberattack, but they do have some challenges in the future. So power systems have been modernized in the past decade or 2 decades a lot. We're integrating more and more renewable generations. So the renewable generations are different with the traditional steam generator, for example. They don't have those large rotating mass, which means they don't provide inertia to the system. So what does that mean? That is the frequency will change faster than the original system. And then we have, on the demand side, we have more distributed energy resources. For example, at California, we have a lot of rooftop solar. And those are what we call behind meter, meaning they're not visible to the operators. So give us challenges to the operation already. So right now, we have more active consumers. There are a lot of options to consume the electricity. And also, for example, they are having more and more electric vehicles. So one thing I want to point out about the tech is we assume the tech is only in demand. So given the past experience in the Ukrainian power system, maybe it is hard to break into the SCADA system itself, but compromise a system component might still be a potential threat. So the combination of those Cybertek on the system might still be an open area to explore. So the main takeaway from this presentation is the power system has been traditionally designed to withstand some level of disruptions. And IoT attack is one of those disruptions. So everything I showed in this presentation has been existing in the system for a long time. And what's more, Cybertek do bring attention to the community of power system. There's a lot of research going on there. So hopefully our work along with this presentation can encourage the collaborations between the community at cybersecurity and the community at the power system. And we do believe those collaborations are critical to the safety of our future power grid. We would like to acknowledge National Science Foundation and Defense Threat Reduction Agency, along with Texas National Security Network, for their great support to our work. Thank you very much for your attention. Please let me know if you have any questions.
Okay, we have time for 1 or maybe 2 quick questions.
Hi, Michael Anderson, UC Berkeley. So you seem to have considered mostly a step change where you just increase the load and then you look at how the grid responds to that. Have you considered oscillation, where maybe you introduce a load and then the grid responds by load shedding, and normally tripping out loads is quite fast and responsive, but reintroducing them is slow. So if you then remove the artificial load that the attackers have created, you could maybe cause an over-frequency excursion. Did you look at that?
Yeah, that's a great point, and thank you for bringing that. We have some back slides. That's actually included in our paper, but we have that result right here. That's something you are talking about. So first, at this slide, the load increased, and then system react to it, and then we decrease that load, remove that load again, and then the frequency go over. However, still we don't see that immediately action from the system. There might be action after this situation lasts for a longer time, but the generator can react by the time. Thank you.
Thank you very much, really interesting. I wonder if your software, if the results are available publicly?
Currently not. The reason is we're applying these two to different systems and realize that the configuration and parameters of that system varies a lot. It gave us already a difficulty to apply the two from one to the other. We think we should make it more easier to use before we put it online.
Yeah, well, it will be really very valuable if it will be made available. Thank you.
Thank you.
Okay, last question while the next speaker sets up.
Tarek Yosef from Google. Has there been any consideration, or have you heard of any cases where you take almost a distributed systems approach, like having, say, protections on the individual meters from looking at like massive spikes in consumption? I was wondering if you can comment on that.
Yeah, so currently we're looking at the transmission system. The reason is we think the backbone of the power system is more important. We're cared about like the safety of the large area customers. But that's a good point, and that's, I think, definitely a future work that we can do on the distribution system and how to isolate the Cybertek like immediately in the small region.
All right, let's thank Bing one more time.
Thank you.
We've had to